8. So it's 8 protons. To get the number of electrons, it's the protons minus the charge. So the 8 minus, charge is minus 2. And that's 8 minus a minus. Minus minus becomes plus. So that would become 8 plus 2. And that is 10. So it does have 10 electrons. So then when we're doing the orbital diagram for that, it's 1s, 2s, and then 2p. All right, so we put in the arrows. The S's only get 2 electrons. And then the last 6 have to go in the 2p. The 2p, you have to put 1 in each box before you start coming back and filling them up. All right, so now we've used up all 10 electrons. So if you count them, if you count the arrows, you'll count 10 arrows. So now I'm going to write, that's orbital diagram there. A lot of times within an orbital diagram, you'll see boxes instead of dashes. And so for the electron configuration, you just write what's underneath the line, and then write as an exponent how many arrows there were. The 2s has 2 arrows in it, and the 2p has 6 arrows in it. Okay? So this is what should be underneath that green stuff, the green arrows, that right there. What I have, some of that is screwed up. All right. Anybody need a second to copy this down? Yes? Okay. Just put in like a finished when you get done. Yes, all P's have 3 slots. Okay, cool. Spencer. How can I help you, Spencer?
Hello there. Can you hear me?
Hi. Yes, I can.
Happy Friday. I think it's Friday.
Yes, it is.
Hey. Spectacular. Did you not just say that oxygen has 11, not 10? Because I'm missing something.
That's before I looked at the periodic table. So
and it does have 10?
It has 10. It does have 10. Oxygen 2 minus has 10. So everything I said before drawing what's on the board now, there was something a little wrong with all of that. And then looking at it, I got a little nervous. And then I forgot the atomic number of oxygen until I went back and looked at the periodic table.
Was 8.
Yes, it's
all right.
8.
I wanted to double check because you said that I missed a little bit, and then that makes more sense now. Thank you very much.
Okay, you're welcome. No problem. All right. And Hunter says, do D's have 10? Yes. So I will. Can we learn how to do the math problems on SmartWork? Yes. I can't do it right now because I got to finish this, but you can learn during office hours. And I'm also going to put up another lecture where I'm going to work problems for you, and you can see how I'm doing it. All right, so there's S, P's, you're welcome, D's, and F's. S's have 1 blank, P's have 3 blanks, D's have 5, and F's have 7. All right, so it's super poodles do fly. And then does anybody see a pattern in the numbers? They're all the odd numbers. Right. So all you have to do is count using your odd numbers, 1, 3, 5, 7, and you don't have to remember the bottom. You just have to remember count in odd numbers, and the top is super poodles do fly. And the numbers correspond to how many dashes you'll draw. So if it's an S, you draw 1, and if it's a P, you draw out 3, like I did there, and so forth. This is called electron configurations. That is a good question. All right, so let me switch back to the notes. Yes, Spencer.
You said earlier to just stop at 7. Does it go higher than that, or will that be like how is it applicable to go higher for electron? What is that?
Technically, they can go into G's, but we're not going to be going into G.
What is it? What is that for? Out of curiosity. Sorry if I'm overstepping.
That's when the electrons get excited into another level. Mm-hmm. So let's say you had one of the lanthanides or actinides, which end in F, and their electrons got excited. They could go up to a G, but it's not common. It's not a common thing that we would work with, and we're not going to do it in this class.
All right. Okay. Just double check.
Sure.
All right. Thank you.
You're welcome. Okay. Now we get back into some stuff that I did right. Okay. So valence electrons are the electrons on the outside, and the core electrons are the electrons that are more inside. Valence electrons, being on the outside, are the ones that get involved in chemical reactions. So they will be shared with other atoms, or they may transfer an electron from one atom to another. But that doesn't happen with core electrons, just valence electrons. And then I wrote down the electron configuration for neon. Neon is a noble gas, and it has 10 electrons. It's atomic number 10. And then I wrote out the electron configuration for that, which if you notice, it's exactly the same as oxygen 2-. Oxygen by itself that's neutral only has 8. Oxygen 2- has 10 because it's added 2 extras. By adding 2 extras, it has the exact same electron configuration as neon, which makes it really stable. And it's also what's called isoelectronic with neon. Isoelectronic just means they have the same number of electrons. And so below that, I wrote the 1s2, 2s2, 2p6, which is just the electron configuration for neon based on its diagram that I wrote above it that has all the little arrows. Below that, I did it for sodium, and I'm going to show you how to do a condensed diagram in just a second. It saves a lot of time when you get down to things like iron. All right, so sodium is 11 electrons. I'm not talking about sodium plus, it's just neutral sodium. It's atomic number 11. So I wrote out the orbital diagram, and because it has one more electron than neon, instead of stopping at 2p like neon did, had to go to the next level, which is a 3s, and put that last electron in there. One thing to note here is that just because the 3s orbital will hold 2, you don't have to put 2 in there. You stop putting arrows when you run out of electrons. So if you count up how many electrons I've put in there, I've only put in 11, and that's because sodium had 11. I didn't fill up the 3s just because it could hold more. And then I wrote out the electron configuration below that. Notice when I wrote the 3s, it's 3s1. All right, so now let's compare those on the next page, just looking at the electron configurations. And looking at nothing else but the electron configurations for neon and sodium. Neon is 1s2, 2s2, 2p6. Sodium starts out exactly the same and then goes one more. 1s2, 2s2, 2p6, and then there's that 3s1 electron. Because neon is a noble gas, and because they've made a way to write sort of an abbreviated electron configuration, we can substitute that 1s2, 2s2, 2p6 in sodium for the abbreviation for neon inside brackets. And what that means, that neon in the brackets, just means in this part of sodium's electron configuration, it has the same electron configuration that neon does. So that neon in brackets stands for 10 electrons. And then the only thing that I write on the outside of it is whatever's left over that did not match neon. And so, and I'll show you in a few minutes when we get to the periodic table how to figure out what noble gas to use there. Generally, you use the noble gas, well, always, you use the noble gas that will replace as many electrons as you can, but you wouldn't want to use something that had more electrons. So you wouldn't want to use, for sodium, you wouldn't want to use a noble gas that had 18 electrons or something, because sodium doesn't have 18 electrons. Can you only use the elements in group 18? Yes, that is correct. You can only use the noble gases. And that's actually called, everywhere else, people call these noble gas configurations. In this book, they call it condensed configuration. So I guess you can call it by two names. So the book, when it mentions condensed configuration, is talking about this noble gas configuration here. They call it a noble gas configuration because it has a noble gas in it, and it's the electron configuration. So they just put those two words together. All right. And then trying to figure out how many valence electrons something has, you can either do the electron configuration and then get it that way, and I'll show you how to do that in a few minutes. Or you can look at the periodic table. So I've sort of drawn a periodic table here. And there are two numbering methods. One goes 1 through 18. And if you look at the periodic table, one of them in your textbook, it will show you two numbering systems. One goes 1 through 18, and the next one goes 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, and the 8 ends in the noble gas. And then you see where the periodic table is kind of sunk down in the middle, where the transition metals are. Those are called Bs. So then it would get like 1B, 2B, all the way to, I don't know, 10 of those, I guess. So when you're looking at it using this system, the 1 through 8, you get a lot more information out of that than the 1 through 18. For example, in red, I've written out the valence electrons for all of the elements in that column. Everything in column 1 has 1 valence electron. Everything in column 2 has 2 valence. Column 3 has 3 valence. Column 4 has 4 valence. Column 5 has 5 valence. 6 has 6, 7 has 7, and 8 has 8. So for those to figure out how many valence electrons there are, you just look at what column they're in, and then that's how many valence electrons they have. And below that, I just did a reminder of that, what's the normal charge it usually makes. So everything in column 1 usually makes +1. Column 2 makes +2. Column 3 makes +3. So far it's the same pattern as you see the valence electrons. Then we skip column 4 because you have to know something else to figure out column 4. We'll get to that later in the semester. And then column 5, instead of being -5, is -3. Then it goes -2, -1, and then neutral. So it goes, the pattern is 1, 2, 3, skip, -3, -2, -1, 0. So if you look below that, if you skip the stuff in red and look to the stuff in blue that says the charges have the pattern +1, +2, +3, skip, -3, -2, -1, skip, or not skip, but neutral. What that's saying is everything in column 1, for example, sodium, normally makes a +1 charge. And things in column 2, like potassium, or not potassium, that's in group 1, like calcium, have a +2 charge, and so forth. All right, the other way to figure out how many valence electrons there are, go back up to the top of the page and you look at sodium. You'll see that it has different n levels, and the numbers are the n level. So when you see 1s2, n equals 1. And then 2s2, n equals 2. 2p6, n equals 2. And then 3s1, n equals 3. So looking at that, let's see. What's the blue writing under column 4? Under column 4, 1, 2, 3, 4. That says skip. Yeah, it says skip. All right. So looking at that, what is the bigger number? 1, 2, or 3? 3. So that's how we're going to figure out what the valence electrons are. The biggest number, you count up all of the things that have 3's on them, and then count how many electrons there are, and that's how many valence electrons there are. So sodium has the highest n level is 3. There's only one orbital with a 3, and so it's just one electron in that orbital, so that's one valence electron. It's a lot easier just to use the column method, but sometimes you have to use the valence electron method from the electron configuration, but that's in the noble, not the noble gases, that's in the transition metals. And we have some more examples of that as we go. All right, so let's look at effective nuclear charge. It's good for this section and it's good for the next section as well. Will we work with the transition metals at all? Yes. Yes, we will. And I'll get into more with the transition metals in just a couple minutes. So with effective nuclear charge, you can think of it on the right-hand side of the page, I've drawn a picture. It's a very bad picture. In brown, you see a fireplace with a chimney, sort of. And then the red there is supposed to be flames. So it's supposed to be a fireplace with fire in it. And then there's an adult standing in front of the fireplace, and they're getting all of the heat from the fireplace. If we don't, we can do it Monday, because 310 is super short. All right, so then you get that the big guy's getting all of the heat. Notice the little guy's getting shielded somewhat. He's not getting as much heat. You look over at the picture of the atom on the left, it's the same idea. The nucleus has the pluses, and those are like the fire. So it's the pull of the nucleus. The electrons in that first circle around the nucleus are like the adult. They're the core electrons, and they are shielding the valence electrons from the full pull of the nucleus. They do get some pull, but they don't get all of the pull, just some. And that's the idea of effective nuclear charge. It means effective nuclear charge. So it's effective nuclear charge, and right next to that in ZEFF is just the symbol that people use for effective nuclear charge. Okay. And then here is a formula for that. The effective nuclear charge is approximately the full nuclear charge, so that's how you count up all the protons, minus however many core electrons there are. So if you look at lithium, lithium has 3 protons. So if you're doing the effective nuclear charge formula, it's the 3 protons minus the core electrons. You can tell which ones are core electrons once you figure out how many valence electrons there are. Figure out the valence electrons and mark the valence electrons out. Everything that's left is a core electron. So the core electrons here, we have 2 of them. So it's 3 minus 2, and that's 1. So lithium's valence electron is shielded, and instead of feeling a 3 proton pull, it only feels the effect of a 1 proton pull, even though there are 3 there. Does that make sense? Yeah? Okay. All right. And then the next section talks very briefly about penetration. It does not go into much detail. You have to know a lot more about structure and bonding to really get into the details of penetration. But the penetration of an electron just means the electron goes a little closer to the nucleus, that penetration of electron closer to the, not electron, scratch that out, right, nucleus. So the electron on the outside gets a little closer to the nucleus than you expected. And this is a beginning to explain how that is, sort of. So for hydrogen, this is the orientation of the levels. Notice it goes ones and then twos, and they're all on the same height. So as you go up, the energy gets higher. So all the two S's and two P's have the same energy. And then the three S's, three P's, and three D's all have the same energy. But that's only for hydrogen. Everything else, it shifts a little bit. So when they're all having the same energy, that's called degenerate. So all of these in one row would be degenerate in energy. They have degenerate energy, meaning they have identical energy. So again, with the electron penetration, it describes how one orbital can overlap spatially with another one, penetrating closer to the nucleus. In other words, where we think something should be in the 2s, sometimes that electron has a small probability of somehow being in the 1s instead. That's called penetration. Look at the difference between hydrogen, where everything was all straight and in a row, and a multi-electron system. Yes, in hydrogen, they can. But in a multi-electron system, they will not be. So as soon as you pass hydrogen, everything gets more complicated. And so when you look at hydrogen, you see everything with the same n level is in the same row. Then you go to something that has more than one electron, and they're all called multi-electron systems, even if there are just two. It goes 1s, 2s, 2p is higher than 2s. So the ones that are degenerate would be the 2px, 2py, and 2pz, but they're no longer degenerate with 2s. The 3s, and then the 3p, and then the 4s. Notice the 3d is between the, I don't know what the matter with me when I drew this out. It should say 4s, and then above that 3d, and then where I have 4p, it should be a 4. I don't normally make this many mistakes in my notes. I don't know what was wrong with me that day. Sorry, guys. So it should go 1s, 2s, 2p, 3s, 3p, 4s, 3d, and then at the top should be 4p. All right. And penetration will affect the energy levels, causing them not to be degenerate to some degree. But that's not the main part of penetration. The main part of penetration you'll see in the electron distribution. And we've seen these maps before. It's just they were separated out into individual maps. Remember when we were counting nodes? Talked about standing waves have nodes, and nodes is where it hits 0. And then we drew the electron distribution map for the different orbitals, and everywhere it hit the bottom, that was a node. So if you look at the 3D orbital, look how much space that covers. The 3D overlaps all kinds of stuff. So it's definitely got penetration in there. And if you look at the 3p orbital, which is in blue, I should have not done blue and green. They're too close. The 3p orbital is just above 3d. And the 3p has 2 humps. And those places where it humps, where it's got a hump in it, that's called penetration. See what time it is. We've got about 5 minutes left. All right. And then this is where we'll leave off, finish this up on Monday. If you want to get a good understanding of this, page 13, if you go back to D12, which I'll show you here. Come on. Maybe, if the computer wants to work with me. And you go to content, and you go down to notes. Where's notes? Click on notes. At the bottom of notes, you'll see periodic table and electron configurations. Take a look at these. And then you see the little link. Some of these links go to really good websites, like the one, the link that's on the page now below this periodic table is a very good link and gives you information on all of this electron configuration stuff. So it's a really good tutorial. It's not an interactive tutorial, but it's good information. And then here's some more information. This I liked because it shows the A-B numbering system. So you see how it goes 1A, 2A, skips the transition metals, 3A, and so forth. And then the transition metals are kind of weird because it starts with 3B, goes all the way up to 8B, which includes 3 columns, and then 1 and 2B are last. So it's kind of weird, which is probably why they switched to the 1 through 18, because people can remember it. It's just not as useful when you're talking about groups 1A, 2A, and 3A through 8A, because you can get a lot of patterns out of that numbering system. But that's where we'll finish up on Monday. And then we'll go through 310, which literally will take me about 5 minutes. It's just talking about how big the atoms are. And that only takes a minute. And then we'll finish up with 311 on Monday. Any questions? Do you want a little more time? How about I make that due on Sunday? Okay, that way I can get the lectures up, and then you can view them and figure out how to do the homework. You will be given a periodic table on the test. So Umar, I'm going to move the homework that's due tonight, make that due on Sunday, and the stuff that was due Sunday, I'm going to make it due Tuesday. So everything's being pushed 2 days. And then push back the 3.6 to 3.10. And then, yeah, the 3.6 to 3.10 is being pushed back a little bit. Should be 3.1 to 3.5 will be due Sunday. And then 3.6 to 3.10, that'll be due on Tuesday. And then the test is going to be just like the quizzes for this test. The next test will probably use ProctorU. And no, I don't think you have to schedule an appointment. I'll have to get more information on that, though. Will you still make the formula list? Yeah, I'm still going to make the formula list. And then, oh no, it's Super Bowl Sunday. Oh, guys, sorry. Adaptive 3A will be due on Sunday as well. Yeah, the adaptives that were due on Sunday get moved, and the adaptives that were due today get moved. So all of the homework due today is now due Sunday. All of the homework that was due Sunday is now due Tuesday. And you'll see, I'll put the dates, I'll put the new dates on there this afternoon after I finish teaching. All right. Anybody have anything else? You're welcome. The quiz Monday covering the quiz